Well, like a cat. Yeah.
You try putting in a
Well,
it works.
1 hour.
This thing.
Yeah. In fact,
Like,
Conserve energy. Just start. Really, here's the nice thing today that we
yeah, I see.
raise awareness of low energy consumption on an hour estimate. Really save energy in this place. Interesting. On a power source. How we can do something to reduce energy consumption. By doing save us money. So I mentioned that later, people are remote conflicts from 8 p.m. to 10 a.m. Local time zone.
Good morning and welcome. My name is Damjan Pelemis, email mailer, and this is talk about Interprocess coordination and communication and how Postgres helps us solve our issues. They sound a little distraught. That's because I am. I just got a big speeding ticket coming from the airport, trying to get just in time. So bear with me. I'll stop and take questions at any time. So this is more of a conceptual presentation. There will be some implementation and some details, but at any point if you want to know more about a certain aspect, definitely stop and discuss that more with you. I want to satisfy your curiosity way more than just present. Okay, so first thing, I work for a mail mailer, and we're a big messaging company. We send newsletters for various big organizations. We push around hundreds of thousands of emails, back, links back. So a lot of data is going back and forth from our system to the customers. This is an overview of what I want to cover this morning. So first, I view of the problem, what we faced, what was our initial analysis, what were the challenges, what did we think we had to overcome. The specific requirements as we refine our process further, we narrow down what exactly our solution needs to address. I'm going to go over the solution itself. So in broad terms and then more specific, since it's a highly technical thing, I didn't put that much code. Again, any questions, I'll jump right into it. Refinements, we actually implemented this a year and a half ago, and as the system started running, we noticed how certain things are not that hard, so we refined it. Drawbacks, we still have some. We identified probably choke points or areas where we can improve and give it a go. And the last thing is the future, or where do we want to take this whole thing. Okay. The building blocks of all our systems are PostgreSQL, so that's our foundation. PostgreSQL for all our data, information storage needs, and Perl for implementing domain logic. There's everything that our system is comprised of. From the outside, we just get a big data pipeline that comes to us in our co-location. The scheduler problem that I'm going to present wasn't actually built for a mailer, it was built for another service. It's for Discuss List, which provides discussion groups to mostly nonprofits and smaller organizations. So I'm going to just give you an overview of what the system does to introduce how we solved it. So this is a very top level view of the system. To discuss this has a web server that communicates with the clients through their browsers. They set up their lists, they add their members, approve their messages, everything that you might think one would want to do with a discussion list. The other big component is the messaging server that other email service through SMTP, either by ingesting the emails that are coming for the list or distributing the messages to the members. Again, the details are not super important, but I'm giving you kind of a clue of why we jump on a solution like this. So the duties of the systems are interacting with customers. HTTP, we're a web service, so customers have to be online to use it, to set up their list, to approve messages, to do basically anything that has an administrative role in the system. So send invitations, send follow-ups, send reminders like your credit card might be expiring, your billing is overdue and stuff like that. Receive and dispatch email, that's the core of the system. So messages come in, they get queued for the list, and they're sent out. And finally, external services such as billing and full-text search. Billing, for billing we interface with, we used to interface with Authorize.net, now we interface with VeriSign or PayPal. So this is a component of the system that charges all our customers. One of the reasons why the scheduler came to be was the slowness of the billing system. Sometimes for Authorize.net, the response time was on the order of seconds. So imagine if you have hundreds of clients and you're doing it sequentially, nothing might see. Full text search, another big performance hog for the messages that come in. Customers want to be able to search them. So just plug in a keyword and find their messages. Another labor-intensive function of the system and best performed asynchronously. So, but this time we knew that one server wasn't enough, so we had to do something more. We had to address the redundancy, the single point of failure. Backup, the customers really don't want to lose their data, so we had to have a system that will take over. And we wanted to future-proof, we wanted to add stuff to support more traffic as we were getting new customers. An average customer would have a few hundred clients, but it grows exponentially as you have to send each email to each customer. Everybody follow that? So onto the wish list or the requirements in general. So we wanted to do real-time load balancing. So all these tasks that I was talking about before, we wanted to somehow split between the systems so that we don't need to add more machines only to find out that some of them are underutilized. So the current workload of the host has to play a factor in the game whereby the work load is being decided. The host-specific scheduling, say for billing or other sensitive matter like full-text search, a host may be targeted specifically because of the file system or because of some other, like for billing security requirement. And finally, tracking. The system must implement task accounting. Some of these tasks take a long time. So if at any point they fail or cannot proceed because of a blocking element, we don't want the entire system to hold, but instead checkpoint and perhaps continue thereafter. So finally, robustness. Once the host goes down or something unpredictable happens, be it a hardware failure, a software failure, a database error, we want to be able to restore to the previous known system. So once restarted, the system should recover if it was a recoverable fault, of course. But we want some way of making sure that the entire system flies all the time. So the first thing that came to mind, of course, was MapReduce and the infamous protocol that follows it. By the way, how many of you have looked or used MapReduce? As an overview, the tenant of the MapReduce and Hadoop, which is an open source implementation of a variation of it, that, for instance, Yahoo uses, is divide and conquer. You have a problem, instead of throwing it at a machine, you slice it, you split the work between the machines, they perform the work, give you stuff back, and you get the output. Well, the nice thing about this is that it scales super well, as these giants have demonstrated. The problem is that at the very beginning, how do you split the problem that's inherently transactional? If you're doing a distributed graph, and you need to find out if a term appears on 5 billion pages, it's fairly easy to see how you can chop up the problem. But say if you need to build somebody, well, it's a transaction. You really can split it up and then track the buses. Instead of one problem, you now have two problems. So this was used as an inspiration, but as the solution to our problem was a no-go. One of the major problems with these approaches was the overhead. The splitting of our specific domain was very incompatible with the idea of maintaining the transactional property of the task. As I said, for billing it's obvious, and for accounting it's a little bit less obvious, but you can still see how the accounting system charges these people per message sent, per subscriber added. Really needs to be robust, especially if all this is happening at the same time. Synchronization was also a big problem. In distributed systems, they almost don't really attempt to synchronize the tasks, as the splitting should have taken care of the sequence in which tasks are performed. Whereas with us, we are mostly pipe and filter flow, meaning once the message comes in, we know what to do with it first, and then ladder, rings, repeat. It's a flow, and it has to be done in a certain way. So we don't want messages to go out before we check if the account is in good standing. We don't want messages to go out to people who are unsubscribed. So we really can do these things out of order. So synchronization was a big problem. I pointed to XML in the end just to quote my teacher, who said that if you have a problem that needs an XML and you decide to go with XML, now you have two problems to solve. Instead of solving just your problem, you're solving an XML problem on top. That's not a slight precisely against the XML, but against the approach of putting a square peg in a round hole. So we decided that we're not going to adjust these systems to our problem, but try to do something different. Edit. And conceptually, and here's where I'm going to descend into more detailed implementation stuff. We have the database that's our Blackboard that hosts all of our stuff. So meaning messages, accounts, users, everything that our system stores is there. Nowhere else. Oh, by the way, when I say Blackboard, do we think the same thing? Do you know the Blackboard architecture pattern? No, yes? It's a very simple thing. It's frequently used in AI, and I'll simplify it a bit. If you have a bunch of workers that are very specialized, say 5 doctors operating, the anesthesiologist will come first, then the surgeon who repairs, then the main surgeon, then another surgeon who will complete, and everything happens on the operating table. So they put their expert knowledge to solve the current step of the problem, and then let it go. The next person comes in, and so on and so forth. So in essence, that's the Blackboard system, and that's what we are trying to do. So we have some data that needs to be transformed, acted upon, or used in some way. And we have our doctors, we have our experts who know how to send mail, how to bill people, how to process the messages coming in, how to deal with the customer who is overdue. And all these doctors are around our database. We call that a worker. So a worker is a specialized worker that knows how to do one thing and does that one thing well. And the scheduler is, well, in my analogy, that would be a person who would direct the order of execution of specific applications. And you can see how this quickly evolves. So you need more workers who do their jobs in a specified order with their expert knowledge. And then, of course, you need more schedulers running on different machines. Perhaps one machine can run more than one scheduler. And then finally, you perhaps have more than one database. One database might hold customer info, another database might hold the CRM info, and that split shouldn't preclude this distributed work from being executed, being finalized. And I'm going to mention what anybody dealing with distributed systems should keep in mind, and it's commonly known as 8 fallacies. I'm mentioning only 4 because they're really pertinent, plus way more than the other. That the network is reliable, that your data is going to traverse the network unaltered, that it will arrive, that latency is 0, that your data is going to be instantaneously appearing in your domain logic, that you can push as much data as you can, and bandwidth is infinite, and finally that the transfer cost is 0. Peter Deutsch of Sun Microsystems is credited for these common fallacies, and these came out of, I believe, mid-80s work on distributed systems. They stand today as they did then. Once the system starts to scale, once you start adding more machines and more workers, these become more and more important to keep track of. Well, now I'm going to dive into the specifics of the scheduler and the worker relationship and show you how we leverage Postgres to implement the system. Well, this is a rough ER diagram of the system. Again, if at any point you're interested in a specific implementation detail, stop and ask me. I'm not going to be sending to those. I'm just going to go over how we solve the problem conceptually. So one major entity that's identified is the scheduler. That we, if you remember the requirements, we wanted to keep track of how they are doing, if they're stalled, if they're dying, if their load is too high. So we track their last notification, which is a dead man switch. If they hadn't posted in a while, we deem them dead. So we kill them and start a new one. ID, of course, to keep track of each specific scheduler, because nothing else is specifically a scheduler. Name allows us to target a specific scheduler for a specific job. And that ties back to the billing system that might be on a more secure box or a more isolated box. We don't want the billing to emanate from any node in the cluster. We just want that specific machine that's designated as the billing server to process our billing requests. The PB is just for the OF, for the time with the last node, so we can kill the process that's running off. The relationship belongs to is obvious, and the worker B that just picks up the task is the entity that encapsulates the expertise I was talking about when mentioning those surgeons. So a worker might pick up a task and process it, report back to scheduler that it's done. And this is the backbone of the system. This is how the work gets into the system, and this is how the work gets out of the system. The specifics of the task might be intricate. Say, a message coming in might need to go through more than one processing stage. Say, a message coming into the system might be decomposed so that we know what it's made out of. So it will have an envelope, and it will have a content, and it will probably have some attachments. So this could be one worker. Then after it's decomposed, another worker might try to determine whether the person sending the message is actually allowed to do so. So if he is on the list, if the list is active, if the customer who owns the list is up-to-date paid customer, he's not overdue, and if he's overdue, we don't want to process that data. So another checkpoint would be the status check. So finally, so these are steps that are performed by different workers. So I'm hoping that you can see how this crystallizes. Instead of having a process do all these steps, we can have highly specialized lean processes that do one task, but one task well. This allows us, say, to have entities like persistent in-memory processes that just collect email, so just ingest email. After the status check, the email goes up. And this could be another worker that pushes the email out to all the current subscribers and takes accounting into the equation and posts that a message has been sent from this user to a list and update all the relevant statistics for that particular list. Question? Following? Okay. So far we have main scheduler who wakes up, picks up the work, and decides which worker to give it to. This waking up mechanism is to listen and notify, and at this stage is a single queue level. So we have a scheduler that's listening to a specific channel, and when the work is being posted either by the main application or another worker, the last step of posting the work is sending a notify signal that wakes up, unfortunately, all the schedulers. Whoever gets to the signal first is going to execute retrieval of the work posted, and this is done through a transaction, which means that a job posting, a work request can only be picked up once. We start the transaction, execute the collection algorithm, pick up the work, tag it as picked up, and finish the transaction. This isolates these steps so that we don't have overlap or it's not run on raise permission. I told you that, didn't I? Well, let's jump into the election algorithm because that's one of the interesting parts of the system. So when a scheduler is started, whether it's on a machine or on the same machine, it's going to register itself into the scheduler's table so the system can keep track of the active schedulers and kill those that have died or clean up after those that have exited incorrectly. It will register for on the listen channel so that it can get notifications from the database. This is one of the big parts for us. Doing multi-threaded development in Perl is prohibitively, what should we put this in polite terms? Hard. Sometimes it even doesn't work as advertised. We even tried this external application that made it even harder. So they all presume that if you're doing some interprocess communication, you really need to shove data back and forth via some remote process invocation or some complex protocol, whereas we, for our workers, we only stop and go. And to include that huge overhead on a fairly small development team was a big deal. So the database really provided a secure and robust channel for these processes to send signals back and forth. And those signals are very simple. It's just job posted, pick it up, or a scheduler died, wake up, pick up the slack. And for the purposes of this system, that worked brilliantly. The main problem being is that it's still a single queue system, which I'll mention when we get to diffusion improvements. But it provides a way for a laddering scheme where you have different priorities listening on a different channel, on different channels, and at the same time you don't incur any overhead because the database does all the work for you. We're already using a powerful database in the backend, and this was a logical choice. And now that I say it, it sounds fairly obvious, but it wasn't. Yeah. The other signal that, the other communication mechanism we're using is from the parents to the children. And when the shutdown notifier occurs, all the children are being told to stop what they're doing, do a checkpoint if they can, or just exit. Finally, keep track of outstanding work. So if a worker has been dispatched and hasn't come back in a while, either kill it, try to checkpoint it, or just see what's going on there and maybe throw some logging into our logging server, so we know there's a problem.
So the scheduler is a one or rather many threaded processes, just pulls the database every, say, 1 second, pull data from the table?
Right. Right. That would be straight polling, and unfortunately, many processes attacking the database at the same time would create a huge overhead. So instead, what we're doing is polling every 5 minutes, so that if there was a work out there, if there was some outstanding work, or if the scheduler had died, it can pick up asynchronously. But if a job is posted, a scheduler would get the notification through the listen notify mechanism of Postgres immediately to wake up. Right. So. Sorry.
What is it? An insert trigger or something?
No, it's built into Postgres. It's
okay.
It's an asynchronous notification mechanism that's built into the server.
Oh, I didn't know that.
It's like a messaging conduit. You get you remember those cans that are connected by a thread? That's how it works. So you get a sender on one side, and you can have many receivers on the other side. And all that it guarantees is that it's going to put it in a queue. Whoever is listening to it is going to try to pick it up, but only one will get it. And that's the key here. If it were sending it to everybody, it would be very bad for us, because then we would have like an army of schedulers trying to lock the job table. Yeah. But here, Postgres is doing the initial election for us, picking up one guy at random who's going to wake up, pick up. Right, but not everybody is executing the query.
But all the list, everybody that's listening on a particular event will get that event notification.
Oh yeah, yeah. It's just who gets to act on it is what we are leveraging.
Right.
They're going to execute a transaction which would guarantee that only one will get to pick the job at a time. As I said, quite obvious. I think this is the most technical thing I have. I don't want to really propose the whole thing. I want to emphasize that it's really not that complicated. What we're doing here is just getting the scheduler who hasn't worked in a while, then ordering them by the number of jobs they have, and this is also a refinement I'm going to mention later, and just picking one. And this will get that lucky guy who's going to try to find a job for himself. So, fairly obvious. Yeah.
I'm a little bit confused on
Sure.
when it sends out the signal and they're all going to pick it up. How do they know? How do you make it so they don't have a race condition? So
It's right there. It's right there. So let's say you have 5 schedulers. They all execute this query, and they try to see they are the lucky one.
Oh, okay.
So dispatching the work, this is just one step further. Again, I'm not going to dive into details of the work itself. So scheduler that was the lucky one, run the work, will spawn the worker and hand it over the reins of control. It's going to tend to say, well, you're the expert, here's the job, you go and run with it. So the worker is being watched by scheduler, which means that if it were to die or have an exception raised or do anything unusual, the scheduler will pick it up, mark the job as being failed or incomplete or maybe 50% done, so that the next one will know what to do next. So this was a brief excursion into what happens after the job has been picked. And I'm going to go into the nitty-gritty of what happens after the election. It's a really good point if you have questions for the process of the system.
Can you back up to this election code?
Yes.
Yeah, this will be.
Oh, yeah.
Yeah, this query, and that query took a long time to get right, so that exactly all agree, and it came up with the same answer on every box. Unique. There's no.
Sorry, can you say that out loud, please?
No, that query just took a long time to get right.
Yeah, not surprised.
There's so many little twists and turns, I think.
We experimented with quite a few ways to get these elections, and the inspiration came mostly from OS schedulers that deal with a similar problem, and to get it right and to get it done simply was a bigger problem.
I could be just messed up in my head, but how would it be different? Like what if, since each one of these things are going to run a select statement at different times,
Right.
what's going to stop one from, just taking a different one, and then the number of workers that it uses increases? So why would it produce the exact same result for every single period? Because everything's asynchronous.
This query is being executed before the work is being done.
Let me say, what if one of them came up, let's say, a second late because
Right.
they were doing something else, and during that time,
Somebody picked up
somebody
the
else
work.
picked up the job, and so now the answer is different. What happened?
Oh, well, ultimately that's not the problem. The work is isolated. So even if the election doesn't yield a single result, the person who comes after is not going to get the same job.
I mean, if I know what happened.
Right. it may try to find work, but if it has already been picked up, it won't find anything. And if it did, then it might be an outstanding job from before. This is really the key. These are the steps, say 1, 2, 3, 4. If somebody picked up 2, the only available work is going to be number 3. Because, the only available work is going to be number 3 if number 2 has finished. And that's perfectly fine. The only thing that we are really worried about is that these are done in sequence. And if the Blackboard system that guarantees this, the next step in the work is posted only after the previous step has finished. Then the next guy coming up is not a problem for us. It's actually a good thing. We are not guaranteeing that the job is being picked up by a single scheduler here, but to the next step. And that's the transaction that I've been talking about before. So basically, start the transaction, pick work, tag work, and then finish the transaction. This is our critical element.
This step basically limits the number of workers that are going to try to take the lock on.
Right. Right. And that's what we're battling with. The contention for a resource that's precious to us. That table that holds all the outstanding work. Does that answer your question?
Helps.
So, sorry, just to clarify. This will, you're still protecting the work task with a lock, right? So you're going to register and say, in effect, I'm doing this piece of work.
Yes.
Right, and what this does is to limit the number of people that is going to try to take that lock, and anybody that gets the wrong result from this isn't even going to try.
Exactly.
Okay.
Well, I hope this clears it up, because I'm going to go into finer details of what happens after the election is being held. I'm well, we started a bit late, so I guess we don't mind if we're 5 minutes over. So, hold the election to decide if we are the one looking for work. And if the result is that if we are the magic scheduler who got the first dibs on the job pool, then mark the action as started, create an entry in active actions, and issue notify schedulers so that other people might look for work. And this, however trivial it sounds, it's almost like that maxim from the arrays. If you reach the end of the array, your best bet is to double its capacity. It sounds counterintuitive, but works really well. It's shown that if we are actively seeking for work, there will be more work. If we didn't get anything, then most likely there is nothing outstanding from that moment. And again, this goes back to the contention algorithm to pick up new work. Robustness, I'm going to just run over this. 2 types of exceptions, fatal and non-fatal. If a task is executed with a non-fatal transaction, we retry. Say we tried to build somebody, the system came back and said, well, try again in 5 minutes. So we'll just reschedule. If it's a fatal, then it goes back to developers and the ticketing system to be sold. So this is just a blend. Refinements, and this is the most interesting part. So we hold the elections and choose our schedulers based on the number of workers, because our tasks and works are very close to the same length. And a refinement would be to jump on and take the load of the scheduler or load of the workers and hold the election based on that. So instead of just saying, well, all the work is the same, maybe some work takes more processing power, more I/O inputs, that's definitely one of the directions we want to take this. Multi-level notifications, like both schedulers, not all work is created equal. Some work is more important. We want priority one for, say, reconnecting the database, and maybe lower priority for sending reminders to members. So we kind of have finer grained control over what's going on in the system. Better track pointing than switch. So instead of just posting what's going on, getting a finer grained track pointing so that we can continue work instead of just reverting to the previous point. But this is domain specific.
Are these refinements that you've done?
No, this is
This is your wish list?
Yes.
Okay. For the load calculation, are you just going to say assign weights to step 1, step 2, step 3, and step 4?
Right. Well, at this stage, this is only conceptual.
Okay.
So when we were talking first about getting the load as the percentage of the CPU load, some smart person said, well, how about the I/O?
That's big. Yeah,
Right.
that's a big one.
And for us, I/O bound tasks are heavier and more blocking.
Yes.
So we had to take that into account. And, I believe that one line is going to take quite a bit of time to get right. But it's definitely one way of getting the work to be distributed equally. We are lucky that our jobs are fairly equal in weight. So that's why it works for us. The whole presentation is going to be on labs.mailmail.com. So you can just download it, you can get the slide, if you saw something that takes your fancy. Well, if you have any questions, I'm willing to. And take it? Why?
At some point, this code will be, the code will also be in labs.mailmail, that kind of with us isolating out our code versus
The domain.
It's very integrated with
Right.
our right now.
So we want to release it as open source. The scheduler and the worker are not that big. The entire code base is the process in the details. How those queries are crafted and how the system works together. And it provides a lightweight alternative to heavyweight distributed systems that most people really don't need. And as Ruby on Rails was mentioned to lowering the bar, this was meant to ease the transition from single box to a multi-box system. And use Postgres in the process. Thank you.
That's fine.